Module 6, Lecture A, Decision Trees. By the end of this lecture, you will be able to explain how decision trees split engineering data into increasingly useful groups, implement a simple decision stump or shallow tree using manual split calculations, and interpret tree rules and identify signs of overfitting in overly deep trees. Tree split intuition. Choosing better splits. An effective decision tree depends on choosing splits that create meaningful groups. The algorithm looks for questions that separate mixed observations into branches where outcomes are more similar. In engineering, this can help group machines by failure risk or materials by strength. Strong splits reduce confusion and make patterns easier to interpret. A decision tree chooses splits by testing which questions best organize the data. These questions may use numerical thresholds or categories, and the tree selects the option that creates the clearest separation. For classification, that means groups mostly contain one class. For prediction, it means values within each group are similar. The goal is to focus on meaningful features that make later decisions simpler. A good decision tree split should reflect the main source of variation in the data and fit the engineering context. After the first strong split, the tree asks more specific questions to refine the groups. The goal is not complexity, but meaningful splits that reveal patterns, improve interpretability, and support more accurate predictions. Python code. Choosing better splits. Compare possible splits by measuring simple impurity in the pump failure labels. A lower weighted impurity means the split creates clearer, more useful branches. We start by importing NumPy to work efficiently with numerical data in arrays and matrices. We also import Matplotlib's plotting tools so we can create visualizations of the data and analysis results. We store vibration measurements in millimeters per second in a NumPy array so they can be analyzed efficiently. This organized data helps compare vibration levels with pump failures and evaluate possible decision splits. Temperature readings are stored in a NumPy array as Celsius values related to pump operation. These readings will help assess whether temperature is linked to pump failure and whether it is useful for splitting the data in the analysis. We use a NumPy array to record whether each pump failed, with 0 meaning no failure and 1 meaning failure. This failure status lines up with related measurements like vibration and temperature, so each pump is tracked consistently. This makes it easier to compare those features with pump failures. This check confirms that the vibration, temperature, and failed pump data all contain the same number of entries. It helps ensure each measurement lines up correctly across the datasets, preventing mismatches that could cause errors in later analysis. The Gini function measures how mixed a set of binary labels is. It first treats the labels as a consistent array, and if there are no labels, it returns 0 impurity. Otherwise, it estimates the probabilities of failure and success, then computes Gini impurity from those probabilities. Lower impurity means the labels are more clearly separated. To measure how mixed the labels are, first find the average label value, which gives the failure probability because failures are marked as 1. Then, compute Gini impurity using the probabilities of failure and non-failure. A value of 0 means the labels are perfectly pure. The function scores a possible data split by dividing labels into 2 groups based on a feature threshold. Values at or below the threshold go to the left group, while higher values go to the right group. This helps measure how well the threshold separates the data, which is a key step in building decision trees. The code first finds the total number of labels, then uses that total to calculate how much data falls into each split. It does this by dividing the number of labels on the left and right by the overall label count. These proportions, or split weights, are then used to judge the split based on impurity. This calculation finds the weighted Gini impurity for a possible data split. It combines the impurity of the left and right groups, weighting each by the share of data points it contains. The result shows how well the split separates the data into distinct classes. We define a set of candidate splits to test how well different questions separate pump failures from non-failures. Each candidate uses either vibration or temperature, with a chosen threshold, such as vibration at 3 or 4 and temperature at 54 or 61. These options will be compared to find the split that best separates the data. An empty results list is used to store each possible split's score, feature name, and threshold. The process checks every candidate split and uses the split score function to measure how well that threshold divides the data. These scores are saved so that different splits can be compared by their impurity. To choose the best split, we compare candidate splits by their impurity scores and select the one with the lowest score. A lower impurity means the data is separated more clearly. The selected result gives the best score, the feature to split on, and the threshold that defines the split. This helps partition the data in a way that can improve predictive performance. We first measure the Gini impurity of the full failed pump dataset to set a baseline. Then we compare possible splits and choose the feature and threshold with the lowest impurity. The final weighted Gini impurity shows how much the best split improves the dataset's purity. The code reviews each candidate split by reading its score, feature name, and threshold. It then prints these values in a clear format with the score rounded for readability. This gives a quick way to compare split quality based on impurity. Choose the data to plot based on the best split found earlier. If vibration is the best splitting feature, plot the vibration values. Otherwise, plot the temperature values. This keeps the visualization focused on the feature that best separates pump failure outcomes. This plot shows how one selected feature relates to pump failure outcomes. The points are colored by whether the pump failed, and a dashed vertical line marks the best threshold for splitting the data. The axes label the feature and the pump outcome, with 0 meaning no failure and 1 meaning failure. The goal is to show that a better threshold creates cleaner, less mixed branches. This script finds the best way to split pump data into failed and non-failed outcomes using vibration and temperature. It compares possible thresholds with Gini impurity, choosing the split with the lowest weighted impurity as the clearest separation. It then reports the starting impurity, the best feature and threshold, and the impurity after the split, while a plot shows how that threshold divides the data. Left branch logic. In a decision tree, the left branch often represents the data that meets a split condition, such as a threshold or range. This is not a fixed rule, but it is a useful way to picture how the tree organizes data. The left branch is a focused subset of records that share the same outcome for that comparison. In a decision tree, the left branch represents one outcome of a split that helps turn raw data into more meaningful groups. For example, pumps with vibration below a threshold might be sent left to indicate healthier operation, while concrete samples with shorter curing times might form a group with distinct strength patterns. The purpose of the left branch is to create a subset that is more consistent or informative than the original data. In a decision tree, Each left branch is part of a sequence of decisions, not a standalone result. Earlier splits shape what that branch means, and later splits refine the data into more specific groups. This makes decision trees useful in engineering because they work like diagnostic questioning, gradually narrowing complex data to support clearer understanding and prediction. Python code. Left branch logic. Decision trees work by asking simple engineering questions that split the data. Rows that meet a condition follow the left branch, and we can inspect a vibration-based split to understand how the tree separates the data. The script begins by importing pandas for working with structured data, such as tables, and matplotlib's plotting tools for creating visualizations. Together, these libraries prepare the code for data analysis and charting tasks. We create a small pandas dataset to represent pump vibration data. It includes 6 pumps, their vibration levels in millimeters per second, and whether each pump is healthy or failed. This simple structure lets us examine how vibration levels relate to pump status. A vibration threshold of 2.5 is used to split the pump data into 2 groups. One group includes rows with vibration below the threshold, and the other includes rows with vibration equal to or above it. This creates a simple Boolean split based on vibration level. We split the pumps by the vibration threshold, then count the status labels on each side. Pumps below the threshold form the left branch, while pumps at or above it form the right branch. These counts show how healthy and failing pumps are distributed across the split. The split asks whether each pump's vibration is below 2.5 millimeters per second. Pumps below that threshold go to the left branch, and their share of the total is counted. The status labels in the left branch are then summarized by count, and the same label summary is created for the right branch, which contains pumps above the threshold. The plot shows each pump's average vibration level as a scatter point, with color indicating whether it is below or above the threshold. A vertical threshold line separates the 2 branches, making it clear which pumps fall on the below threshold side. The axes identify vibration levels and pump identifiers, while the title and legend clarify the meaning of the split and the colors. This script uses pump vibration readings to show how a decision tree makes a simple split. It separates pumps at a threshold of 2.5 millimeters per second, placing lower readings on one branch and higher readings on the other. It then counts healthy and failing pumps in each branch and plots the result, showing how a basic condition can divide data into meaningful groups. Right branch groups. In a decision tree, the right branch represents cases that do not satisfy the split condition, not cases that are less important. It captures a different region of the data, such as warmer machine readings or high vibration pump behavior. These groups can reveal useful patterns like possible bearing wear or maintenance needs. Overall, splitting helps create more internally similar groups, improving both prediction and explanation. A right branch in a decision tree is useful when it isolates cases with meaningful engineering behavior, not just leftover data. For example, it may group rougher manufactured parts or heavily loaded road segments, so engineers can examine higher-risk conditions more closely. By narrowing the context, each branch supports more focused questions and more informative decisions. In a decision tree, the meaning of a right branch depends on the split that created it and the earlier splits along the path. Higher branches often capture broad conditions, while deeper ones describe more specific situations. A branch is useful when it creates clear, reliable groups, not just when it isolates a few unusual cases. Good interpretation asks whether those groups are large and stable enough to support meaningful conclusions. Python code. Right branch groups. In a decision tree, right branches gather cases that exceed a chosen threshold. Small engineering datasets can make this behavior easier to understand, and simple manual counts help reveal useful patterns within the grouped cases. The script imports pandas for working with structured data, and matplotlib for creating visualizations. Together, these libraries provide the basic tools needed for data analysis and plotting in Python. We create a small pandas dataset to represent pump observations. It includes vibration measurements and a wear risk label for each pump, marked as low or high. This lets us explore how vibration levels relate to the likelihood of wear. A threshold of 3.5 is used to split the data by vibration level. Rows with vibration above the threshold form the higher vibration group, while rows at or below it form the lower vibration group. This makes it easier to compare pump behavior across different vibration intensities. Count the pumps with high wear risk in both the right and left groups by checking the wear risk column. Comparing these counts shows how high-risk cases are distributed across the two branches and helps evaluate the threshold-based split. To measure branch purity, calculate the percentage of high-risk cases in each branch. For both the right and left branches, divide the number of high-risk cases by the total cases in that branch. Then convert the result to a percentage. These values show how strongly each branch represents high wear risk cases. The code summarizes a split based on vibration level. Pumps at or below the threshold go left, while the rest go right. It reports how many pumps are in each branch and the percentage with high wear risk. The key takeaway is that the right branch represents warmer, riskier operating conditions, making the split useful for understanding pump behavior. The visualization assigns colors to wear risk levels, using steel blue for low risk and tomato red for high risk. A clear scatter plot then places vibration values along the horizontal axis, with all points aligned on one level vertically. Each point's color shows its wear risk, making it easy to see how risk varies across the vibration range. Add a dashed black vertical line to mark the split threshold between the left and right groups. To keep the plot clear, remove the y-axis ticks and label the x-axis as pump vibration in millimeters per second so the data is easy to interpret. The plot is finalized by adding a clear title that highlights vibration levels above the threshold on the right branch. A legend explains the color coding for wear risk levels, and the layout is adjusted so all elements fit cleanly. The completed plot is then displayed to help analyze pump vibration patterns and related wear risks. The script uses a simple decision tree to assess pump wear risk from vibration data. It splits pumps at a threshold of 3.5 millimeters per second, then compares the share of high-risk cases on each side. Pumps above the threshold show a higher concentration of high wear risk, suggesting they operate under riskier conditions. A scatter plot supports this by showing the threshold and the separation between low and high-risk cases. Choosing tree splits. Categorical split calculations. For categorical features, a decision tree splits records by category rather than by numeric thresholds. It checks whether groups such as different production lines have different outcomes, like defect rates. A split is useful when one category shows a clear pattern, but it adds little value if all categories have similar results. To evaluate a categorical split, count the observations in each category and compare how the target outcome is distributed within them. For classification, look for categories that separate classes more clearly, such as one mode having a higher failure rate. For regression, look for categories where target values are more tightly grouped. A good split creates groups with more consistent outcomes than the original dataset. When splitting categories in a decision tree, you can create separate branches for each category or use binary splits that compare one category or group against all others. A split should not be judged only by improved purity or lower error because small category counts can make results unreliable. Good split selection combines numerical measures with judgment about whether the data is sufficient and likely to generalize. Python code, categorical split calculations. Manual categorical splits can reveal useful engineering groups. In this small pump maintenance example, the key idea is to compare impurity before and after a split to judge whether the grouping improves the data separation. The script begins by importing pandas for working with structured data, such as tables, and matplotlib's plotting tools for creating visualizations. Together, these libraries prepare the environment for data analysis and visualization tasks. We create a small pandas dataset to study pump failures under different operating modes. It includes the pump mode, such as normal, high load, or standby, and a failure indicator where 0 means no failure and 1 means failure. This simple setup helps compare how operating conditions relate to the chance of pump failure. We first confirm that the dataset has exactly 12 entries, making it small and easy to review. Then we check for missing values by counting any null entries across the data. Together, these checks show that the dataset is complete and ready for analysis. The Gini function measures how mixed a set of binary outcomes is. It counts how often each value appears, finds their proportions, and uses those proportions to calculate Gini impurity. A lower result means the data is more pure, with less diversity among the outcomes. Before making any splits, we measure the overall impurity of the dataset using the Gini function. Pause. This is applied to the failure outcome column, which records whether a failure occurred. Pause. The resulting parent Gini value represents how mixed the dataset is before any categorical split is considered. The code summarizes the data by mode, counting the entries and total failures in each group. It then computes each mode's failure rate, measures the impurity of failure outcomes using the Gini function, and calculates each mode's weight based on its share of the full dataset. To judge a split, calculate the weighted Gini impurity by combining each category's impurity according to its share of the data. Then, find the Gini gain by subtracting this weighted impurity from the parent impurity. A higher Gini gain means the split made the resulting categories purer than the original dataset. The output compares Gini impurity before and after splitting the data by pump mode. It reports the parent impurity, the weighted impurity after the split, and the resulting Gini gain, each rounded for easy reading. It also summarizes each pump mode by entry count, number of failures, and failure rate, helping show how well the split separates different failure patterns. We visualize failure rates for each pump operating mode with a bar chart to compare categories clearly. The chart uses the failure rate values from the summary data, labels the axes for operating mode and next week failure rate, and scales the vertical axis from 0 to 1 for percentage style values. After adjusting the layout, the plot is displayed so the differences in failure risk across modes can be assessed visually. This script evaluates how pump operating mode relates to failure risk using Gini Impurity. It first measures the overall impurity of the failure data, then compares it with the weighted impurity after grouping the data by mode. The difference, called Gini gain, shows how much the mode split improves separation of failure outcomes. A bar chart then summarizes the failure rate for each mode, making the effective operating mode easier to compare. Candidate split calculations. In decision trees, candidate split calculations test possible thresholds for numerical features to turn broad questions into clear rules. Rather than splitting at every observed value, the tree checks points between ordered values and chooses splits that make the resulting groups more informative. For example, a threshold on vibration or part thickness can help separate normal from faulty equipment or acceptable from defective items. To evaluate a candidate split, sort the data by the feature being tested and consider thresholds where the target changes. Each threshold divides the data into two groups, which are judged by how much uncertainty they reduce. For classification, better splits create groups mostly containing one class. For numerical prediction, they create groups with outcomes that are close together. When calculating candidate splits by hand, evaluate each threshold in the same systematic way. Split the data, summarize the target values, measure impurity or variation, and compare the result with the original data. This keeps the choice evidence-based rather than based on assumptions. Practicing this process shows how decision trees automatically search across features and thresholds to find the most useful split. Python code, candidate split calculations. Manual split calculations help show how a decision tree chooses between possible splits. Using a tiny engineering dataset keeps the arithmetic easy to follow, while Gini Impurity measures how mixed the classes are at each split. We import pandas to work with tabular data and make datasets easier to manage and analyze. We also import Matplotlib's plotting tools to create charts and visualizations that help present the data clearly. We create a pandas data frame to organize the data for analysis. It includes vibration readings in millimeters per second and matching binary failure labels showing whether a failure occurred. This structure lets us examine how vibration levels relate to failures in the later analysis. The code verifies that the data frame has 8 rows and 2 columns before any further calculations. This quick check confirms the data is in the expected structure, and it raises an error if the setup is incorrect. The Gini function computes Gini impurity for a set of binary labels. It first checks how many labels are present, and if the input is empty, it returns 0. This prevents division by 0 and lets the function handle empty data safely. To compute Gini impurity, first find the share of positive labels, then use 1 minus that share to get the negative probability. The impurity is 1 minus the squared probabilities of the positive and negative classes. This value shows how mixed the labels are, with lower impurity meaning a purer split. The data is first sorted by vibration readings, so possible split points can be evaluated in order. The sorted vibration values and their matching failure labels are then stored as simple lists. This prepares the data for choosing thresholds and judging how well each potential split separates the outcomes. To find possible split points, take the sorted vibration readings and look at each pair of neighboring values. For each pair, compute the average to get a midpoint, which becomes a candidate threshold. These candidate thresholds are collected for later evaluation. We create an empty results list, then test each threshold by splitting the sorted data into 2 groups based on vibration level. Values below the threshold go to the left group, while values at or above it go to the right group. This lets us compare how well each threshold separates the data by failure label. For each possible threshold, we calculate the Gini impurity of the left and right groups to measure how mixed their classes are. We then combine these values into a weighted Gini impurity based on the size of each group. Finally, we store the threshold, group sizes, and weighted impurity so the splits can be compared and the best ones selected. We use pandas to create a new data frame that summarizes the split calculations. Each row records a threshold, the number of observations on each side of it, and the weighted Gini impurity for that split. Clear column names make the results easier to review and compare. To choose the best split, find the threshold with the lowest weighted Gini impurity, since it creates the purest split in the data. Then compare this result with the Gini impurity of the full dataset before splitting. This baseline shows how much the chosen split improves the data's purity. First, calculate the parent Gini impurity to measure how mixed the full dataset is before splitting. Then compare the candidate splits and choose the vibration threshold that gives the lowest weighted Gini impurity. Report the selected threshold and its weighted Gini value using rounded values to make the result easy to interpret. This plot compares candidate vibration thresholds with their weighted Gini impurities after a split. The points show each threshold's impurity value, and a red dashed vertical line marks the best threshold, where impurity is lowest. Clear axis labels, a title, and a light grid make the visualization easier to interpret. This script finds the best vibration threshold for separating failure labels using Gini impurity. It sorts the readings, tests possible split points between consecutive values, and calculates the weighted impurity for each split. The threshold with the lowest impurity is selected as the best decision rule. It also reports the parent impurity and visualizes how impurity changes across thresholds, highlighting the best split. Ranking candidate splits. After calculating possible splits, rank them by how well they make the resulting groups more predictable and homogeneous. In classification, a good split creates branches that mostly contain the same class, while in regression it groups values that are close together. The goal is to choose the most informative question to separate the data first. To rank candidate splits, compare them using the same quality measure for every option. In classification, choose the split that best reduces class mixing. In regression, choose the one that best reduces variation within each branch. For a pump maintenance example, the best split is the feature, such as temperature, vibration, or age, that most clearly separates maintenance cases from non-maintenance cases. Overall, select the split that improves the grouping most compared with leaving all data together. When choosing between similar splits, do not rely only on the score. A split with a slightly better score may be less useful if it creates a very small branch, depends on noisy or rare data, or is hard to interpret. In decision stumps and shallow trees, each split matters a lot, so balance improvement with sample size, interpretability, and measurement reliability. Python code. Ranking candidate splits. Use manual impurity calculations to compare possible splits in the small pump data example. The key idea is that a split with a lower weighted Gini score is considered better. The script imports pandas to manage the dataset as a data frame for easier data handling and transformation. It also imports matplotlib's plotting tools to visualize the candidate split rankings, showing the weighted Gini impurity scores in a clear graphical form. We create a small pandas dataset to represent engineering maintenance data. It includes temperature readings, vibration measurements, and a binary maintenance label, where 0 means no maintenance is needed and 1 means maintenance is required. This simple structure keeps the example easy to analyze and suitable for demonstration. An assertion confirms the dataset has exactly 8 rows and 3 columns. This keeps the example small and verifies the setup before any further analysis. The Gini function measures how mixed a set of labels is. It counts how often each label appears, finds each label's probability, and returns 0 if there are no labels, to avoid division by 0. It then calculates Gini impurity as 1 minus the sum of the squared label probabilities. Lower impurity means the labels are more homogeneous. This code handles the case where there are no labels to evaluate. If the label count is 0, it returns a Gini impurity of 0, avoiding division by 0 and unnecessary calculation. To find Gini impurity, first determine how common each label is by comparing its count to the total number of labels. Then subtract the sum of the squared label proportions from 1. A lower Gini impurity means the labels are more uniform. The weighted Gini function measures how well a feature threshold splits the data. It separates rows into a left group with values at or below the threshold and a right group with values above it. These two groups are then used to evaluate the split by comparing their Gini impurity. To evaluate a split, we calculate the weight of each subset as its share of the original dataset. The left and right weights show what proportion of data points fall on each side of the threshold. These weights determine how much each subset contributes to the overall impurity score, helping judge how well the threshold separates the data. To evaluate a split, calculate the Gini impurity for both resulting groups. The left group contains rows with feature values at or below the threshold, and the right group contains rows above it. By measuring how mixed the needs maintenance labels are in each group, the Gini scores show how well the split separates the classes. This calculation gives the weighted Gini impurity for a possible split. It combines the impurity of the left and right subsets, weighted by how much data each contains. The result is one score for the split, where a lower score means a better separation. A set of candidate splits is defined, where each option pairs a feature with a threshold value. For example, a split might test whether temperature or vibration is below a chosen cutoff. These candidates are then compared using Gini impurity to find the split that best separates the data. The process evaluates each candidate split by pairing a feature with a threshold and calculating its weighted Gini impurity. Each result is stored with its feature, threshold, and score, so the splits can later be ranked by how well they reduce impurity. We create a pandas data frame to organize the candidate split results, including each feature, its threshold, and the weighted Gini impurity. The data frame is then sorted by weighted Gini in ascending order, so the lowest impurity, and therefore the best candidate splits, appear first. The output first announces that candidate splits are being ranked, with lower Gini impurity indicating a better split. The ranked results are then converted into a clean text display without row indexes, making it easier to compare each feature, threshold, and weighted Gini impurity. The code selects the top-ranked split from the data frame, which has the lowest weighted Gini impurity. It then prints the feature and threshold for this best split, describing the decision rule as splitting when the feature is less than or equal to that threshold. This identifies the split that most effectively separates the data based on impurity. Create clear plot labels by combining each feature name with its threshold value, using a less than or equal to phrase to describe each bar. Then set the plot size to make the ranked impurity scores easy to read. We create a bar chart to compare candidate decision stump splits. Each bar is labeled with the feature and threshold for a split, and its height shows the weighted Gini impurity calculated for that option. The chart uses a clear y-axis label and title, so it is easy to see which splits have lower impurity scores. The code improves the plot's readability by rotating the x-axis labels and aligning them to the right. It then tightens the layout so all elements fit cleanly and displays the plot to help compare the ranked impurity scores of the candidate splits. This script compares possible decision splits in a small engineering maintenance dataset using weighted Gini impurity. It tests temperature and vibration thresholds, ranks the candidates, and identifies the split with the lowest impurity as the best choice. The results are summarized in a table and bar chart to show which split separates the data most effectively. Tree limits. Overfitting warning signs. A decision tree works best when its rules capture patterns that generalize beyond the training data. Overfitting happens when the tree becomes too deep and starts memorizing small, specific details instead of broader structure. In engineering, useful splits might involve factors like temperature or vibration, but overly specific splits based on rare sensor readings may reflect coincidence rather than reliable patterns for new cases. A major sign of overfitting in a decision tree is a large gap between strong performance on training data and weak performance on new data. The tree may look reasonable branch by branch, but extra small splits can make it learn random quirks instead of real patterns. This can happen in areas like customer churn, medical screening, or traffic prediction, where a model that fits past cases too closely fails to generalize. Overfitting in decision trees often appears as rules that are too specific, difficult to explain, or inconsistent with domain knowledge. Warning signs include unusual thresholds, rare condition combinations, very small leaf groups, and splits that seem unstable. Even if these rules fit a few cases perfectly, they may be capturing noise rather than real patterns, so simpler and more reliable rules are usually preferred. Python code, overfitting warning signs. Decision trees can overfit by memorizing noisy engineering measurements, so validation checks are important for spotting warning signs. In many cases, simpler, shallower rules generalize more reliably. The script begins by importing NumPy for efficient numerical work with arrays and Matplotlib's plotting tools for creating visualizations. Together, these libraries prepare the environment for data manipulation and plotting. We create a reproducible synthetic machine dataset using NumPy's random number generator with a fixed seed. The data includes 60 simulated temperature readings from a normal distribution centered around 82 and 60 vibration readings centered around 4.8. Together, these values mimic real machine measurements for temperature and vibration. Failures are labeled using a simple rule based on sensor readings. High temperature or excessive vibration indicates a potential failure. Random noise is then added by giving each case a 12% chance of changing that label. An exclusive OR operation applies this flip when noise is present, and the final result is stored as 1 for failure and 0 for non-failure. The data is split by using the first 40 indices for training and the next 20 for validation. This lets the model learn from one part of the data and then be evaluated on a separate part, helping measure how well it generalizes to unseen examples. The data is prepared for modeling by combining temperature and vibration into a two-dimensional feature matrix, where each row represents one data point. The failure status is stored separately as the label for each row. This structure makes the features and labels easy to use for training and validating predictive models. This function predicts failure using a simple temperature rule. If the selected temperature values are greater than 86, it predicts a failure with a 1. Otherwise, it returns 0. This shows how a basic threshold can classify data based on one feature. The deep predict function first uses the stump predict function to make initial predictions, then adjusts them by comparing each row with the training data. If a row has temperature and vibration values close to a training example, it copies that example's failure status as the prediction. This can capture very specific patterns, but it may also overfit by memorizing noise in the training data. We compare each model's predictions with the actual outcomes on both the training and validation data. The shallow decision stump shows how well a simple rule fits and generalizes, while the deep tree shows how well a more complex model fits and generalizes. Comparing training and validation accuracy helps reveal whether the deep tree may be overfitting. First, count the training samples by checking the size of the training index. Then compare training and validation accuracy by finding how much higher the training accuracy is. A large gap suggests overfitting, meaning the model may be memorizing the training data instead of generalizing well to new data. The model comparison prints training and validation accuracy for both a simple decision stump and a deeper decision tree. The deep tree may score very well on training data, but its validation accuracy and the gap between the two scores reveal whether it is overfitting. A large gap, especially along with many tiny leaves, triggers a warning that the model may be memorizing the training data instead of generalizing well. This visualization plots training data with temperature on the horizontal axis and vibration on the vertical axis, coloring each point by whether a failure occurred. A green dashed vertical line at 86 degrees Celsius marks the simple decision boundary used by the stump predictor. The labels, title, and legend emphasize the main warning. Using many tiny rules can overfit by memorizing noise rather than learning a reliable pattern. This script shows how overfitting can occur in decision trees using synthetic temperature and vibration data. A simple temperature-based rule performs similarly on training and validation data, showing that it generalizes well. A more complex model memorizes the training data, giving high training accuracy but poor validation accuracy. The main lesson is that simpler models can often predict new data better, while overly complex models may learn noise instead of real patterns. Overfitting signs. Overfitting in a decision tree happens when the tree becomes too complex and creates overly specific splits. Instead of learning broad patterns, it may focus on rare sensor readings or other details that reflect noise. When a rule describes a unique case rather than a general trend, the model is likely memorizing the data instead of learning from it. A decision tree may be overfitting when it performs much better on training data than on new data. This often happens because the tree learns overly specific rules based on noise or exceptions in the original dataset. The model is not necessarily useless, but some of its patterns may not generalize well. So a good tree should capture relationships that remain reliable beyond the data it was trained on. To detect overfitting in a decision tree, look at whether deeper splits make practical sense and improve interpretation. Good splits should reveal meaningful differences, such as separating high-risk from low-risk cases. If later rules seem arbitrary, lack domain support, or change with small data changes, they may be fitting noise rather than real patterns. Reliable trees should use simple, well-supported rules that are likely to hold for future decisions. Python code overfitting signs. Compare shallow and deep decision trees using a small engineering dataset, so the results stay easy to read. Shallow trees tend to give simpler, more general rules, while deep trees can overfit by creating fragile rules that match specific cases too closely. We import NumPy for efficient numerical work with arrays and calculations, and use Matplotlib's plotting tools to create graphs and visualize data trends. We create reproducible sensor data by using a seeded NumPy random number generator. Then we generate 24 evenly spaced Celsius temperatures from 55 to 95 degrees, giving a controlled set of readings for analysis. A vibration pattern is generated using random values from a normal distribution, with 24 simulated sensor readings centered around 3. A risk score is then calculated by combining temperature with vibration, giving vibration a much stronger weight. This models failure risk, where higher temperature and especially higher vibration increase the score. Machines are labeled as failed when their risk score is above 105, producing a true or false failure label for each machine. To mimic real inspection mistakes, the labels for machines at indices 5 and 18 are then flipped, adding a small amount of noise to the data. The dataset is split into training and validation parts using separate index ranges. The model trains on the first subset and is evaluated on the second, which helps measure performance and check for overfitting. The stump predict function compares each input value with a threshold and returns whether it is greater. This creates a simple decision rule known as a decision stump, which is a one-level decision tree that makes predictions using a single feature. This function imitates a deep decision tree by memorizing the training data. It stores each training index with its label, then checks new input indices against that stored information. If an index is not found, it returns false. The result is a model that can match the training data exactly, but may perform poorly on unfamiliar data. A temperature threshold of 78 is used as a simple rule for predicting machine failure. Any training or validation example above this threshold is classified as a fail, and the rest as a pass. Applying the same rule to both datasets lets us compare how well this basic threshold-based model performs. This example simulates a deep learning model that simply memorizes its training data. The deep predict function stores each training example's index with its failure label, then uses that lookup to make predictions. When applied to validation data, the model can only rely on what it memorized from training, showing how overfitting can lead to strong training performance but poor generalization to unseen data. We evaluate both the shallow and deep tree models by measuring accuracy on the training and validation data. For each model, we compare its predictions with the true failure labels and calculate the share of correct predictions. Comparing training and validation accuracy helps show how well each model generalizes and whether it may be overfitting. The shallow model uses a simple rule: predict failure when temperature is above 78 degrees Celsius, then compares its accuracy on training and validation data. The deep model instead memorizes each training example with a separate rule for each machine, and its accuracy is also checked on both datasets. If it fits the training data perfectly but performs poorly on validation data, that is a clear warning sign of overfitting and weak generalization. This visualization compares machines that passed and failed inspection using temperature on the horizontal axis and vibration on the vertical axis. A dashed vertical line marks the temperature threshold used by a shallow model to split the data. Labels, a title, and a legend make the plot clear, emphasizing the contrast between a broad decision rule and overfitting through memorized leaves. This example shows overfitting with temperature and vibration data by comparing two predictors. A simple decision stump uses one temperature threshold and gets reasonable results on both training and validation data, while a deeper model memorizes the training cases perfectly but fails on validation. The main lesson is that perfect training accuracy combined with weak validation performance is a clear warning sign of overfitting. Rule reliability. Rule reliability in decision trees means judging whether a rule reflects a real pattern rather than a coincidence in the training data. A rule is more trustworthy when it applies to many cases and continues to make accurate predictions on new data. If it is based on only a few unusual examples, it may be capturing a fluke instead of a meaningful relationship. To judge whether a decision tree rule is reliable, look at whether it is broad, stable, and meaningful. A good rule should apply to enough cases, remain consistent when the data or model changes, and make sense based on domain knowledge. Rules based on arbitrary patterns may be mathematically valid but misleading, so model results should always be checked with practical judgment. Deep decision trees can create rules that look precise but are unreliable because they overfit small quirks in the data. A rule is more trustworthy when it is supported by enough examples, works well on test data, and cannot be replaced by a simpler explanation. Reliable rules should be understandable and useful for future decisions, not just accurate on past data. Python code, rule reliability. A rule is only reliable when it is supported by strong evidence. Small details, such as tiny leaves, can mislead engineers, so validation checks are needed to expose rules that may be fragile. The script starts by importing NumPy and Pandas, two core libraries for data work in Python. NumPy supports numerical operations and random number generation, while Pandas helps manage and manipulate tabular data. We create a small, reproducible inspection dataset by using a fixed random seed and setting the dataset size to 40 rows. The vibration values are generated from a normal distribution centered at 5 with a standard deviation of 1.2, giving realistic but controlled sample data. The dataset is expanded by adding random temperatures centered around 72, along with a randomly assigned day or night shift for each row. A failure flag is then created when the combined vibration and temperature measure passes a set threshold. This introduces an unusual training coincidence, making the data more complex. A Pandas data frame is created to organize the data into columns for vibration, temperature, shift, and failure status. The failure status is first based on vibration and temperature conditions, then manually changed for 2 specific rows to simulate anomalies. These added unusual cases help test how well the rules handle unexpected data. The dataset is split into training and validation parts. The first 28 rows are copied for training, and the remaining rows are copied for validation, so the original data is not changed. A check confirms that both sets are large enough for meaningful analysis. 2 rules are used to analyze vibration patterns in the training data. The broad rule flags cases where vibration is greater than 5.4, capturing a wider range of situations. The narrow rule is more specific, requiring vibration greater than 6.1 during the night shift. Together, these rules compare broader and more focused patterns and help assess their reliability. The rule report function summarizes how well a rule performs on training and validation data. It counts how many records each rule covers in both datasets, then measures accuracy by averaging the fail values for the covered records, using 0 when no records are covered. The function returns the rule name along with its support and accuracy for both datasets, making it easier to compare rule performance. We apply the same two rules to the validation data to check how well they hold up. One rule flags cases where vibration is above 5.4, and the more specific rule flags night shift cases where vibration is above 6.1. We then use the rule report function to compare each rule's performance on the training and validation datasets, helping assess their reliability and accuracy. The output begins by noting that rule reliability for inspection failures is being checked. It then reviews each report and summarizes the rule name, how many training and validation samples it covers, and the failure rates in both datasets. These metrics make it easier to compare which rules are more reliable based on their support and accuracy. The lesson concludes that reliable rules need enough supporting data, strong performance on new data, and engineering plausibility. It also warns that overly narrow rules may reflect coincidences in the training data, rather than real, stable mechanisms, which can lead to misleading conclusions. This script tests two hand-built rules for predicting inspection failures from vibration and temperature data. It creates synthetic data, splits it into training and validation sets, and compares each rule by its support and accuracy. The broader rule usually applies to more cases, but may be less precise, while the narrower rule may look strong on training data, yet risk overfitting. The main lesson is to judge rules by validation performance, enough support, and engineering plausibility, not just by patterns that may be coincidences. In this lecture, you learned to explain how decision trees split engineering data into increasingly useful groups, implement a simple decision stump or shallow tree using manual split calculations, and interpret tree rules and identify signs of overfitting in overly deep trees. In the next lecture, Lecture B, we will go over k-means clustering.
Thank you for your attention. See you all in the next lecture.